Hey everyone, so in this video we're going to be looking at graphs and their application in digital fabrication. Digital fabrication has many different types. In general, these are some of the most commonly used machines for digital fabrication. So there are CNC machines, which can be both planar or multi-axis. There's laser cutting, 3D printing, both resin and extrusion printing, water jet cutters, multi-axis robotic arms, which can fit under the umbrella in general of CNC. I am a CNC plasma cutting instructor, and so this is what we're going to be focusing on for the application of graphs with digital fabrication. Here I have a typical workflow of any kind of plasma cutting project. So in general, you're going to come up with an idea, which could be a drawing, something digital or something physical. And then you're going to take that idea and convert it to a digitized vector file. Vector files are different from raster files in that the lines are calculated using formulas and they can be infinitely scaled or minimized, where rasters are just pixel point representations of something. So after you have a vector file, then you can use a CAD software specifically for any kind of CNC output. A very common one is the Autodesk Fusion 360 software, and those can convert it to G-code for whatever CNC machine you're using, and then you take that output G-code file, you put it into the axis controller, specifically here for the plasma cutter, which will give it XYZ coordinates for every cut and give all of the paths from your vector file and convert it to the physical space. And then you can run a couple simulations. If everything looks good, then you can finally cut your material. Plasma cutting is specifically designed for cutting metals. The types of metals are in general any kind of conductive metal. Mostly it's used for mild steel, stainless steel. You can also cut aluminum and copper with it. A plasma cutter is very similar to a laser cutter in the way that it's planar and that there's no extra depth to it. Other CNC machines are capable of depth, but in this case, the CNC plasma cutter is just going to cut out one depth, which is usually the depth of the material. So how does plasma cutting relate to graphs? In creating the vector files that are then converted to G-code for toolpath, the vectors are node-based, and you can see in the representation image with Hello World on the side, which is just something that I made very quickly in Adobe Illustrator. The dots in the image represent the nodes from which the formulas for the lines are created, and they have spatial relationships with each other, with the Cartesian plane that they're on, and then can be converted to the units of whatever physical plane, the size of the plane that you're using, the plasma bed, and then can be scaled for preference. In creating toolpaths, there are a lot of variables that need to be taken into account. In general, the most important ones are the cut time, heat penetration, order of cuts, interior versus exterior cuts, curve width, and the thickness of the material, which can be determined by the type of material and its electrical resistance in ohms. So for all of these paths, nodes can only be cut through once with the plasma cutter, and same with the edges, they can only be cut through once. The paths are usually generated in a way that follows Euclidean and Hamiltonian cycles. And you can see two examples here, specifically in relationship to heat penetration. Heat penetration is very important to consider when creating the actual tool path. When a path is prioritized for shortest distance, you have a lot of heat that fails to dissipate. This can cause many issues, primarily loss of precision or the melting of the material that you're trying to cut. And so sometimes what might seem like the most obvious path is actually detrimental for the outcome that you're looking for. On the right, you can see a path that is optimized for heat dissipation. And this becomes really important when you're working on thinner materials. Thicker materials can dissipate heat faster throughout the entire space of the material that you're cutting. But when you're working with thin materials, the plasma cutter cuts so hot at 40,000 degrees Fahrenheit that it is very easy to simply melt through material instead of just cutting it. So this relates to what we've been learning about in this unit with Hamiltonian Eulerian cycle paths, where tool paths are going to fulfill both of these requirements, in that they should only cut on one edge once and should complete into a closed shape. Usually you have multiple iterations of Hamiltonian cycles and Eulerian cycles within each cut project, unless you're doing a line drawing, but even then it still must be a complete cycle, as the toolpath will not cut if there is not a complete cycle path. Meaning if there's an open shape, it cannot be a cut toolpath. So there are many conditions which toolpaths must meet, but these are some of the most important consideration. In path optimization, there is something called the traveling salesman problem, which is where a salesman is going on a sales tour and he needs to visit each of these cities in the country and must find the shortest path possible. So there's a few ways to solve this, but in general, the simplest but not necessarily least tedious approach is to draw every path that exists for the number n vertices, and then the distance of each edge, total them up, and then find the sum that is the shortest. This becomes really impractical when you have a large number of vertices. So this is a really commonly studied optimization problem for computer science theory and also in math. In general, this becomes really complex, especially when you add path optimization to numerous other variables which are present in CNC machining. So CNC machining algorithms are not necessarily accessible in terms of open source modification. This is a big simplification of path optimization for CNC machining, but you can see once you add in every other possible variable for cutting how complex the machines can get. And then also some of these variables are not able to be measured consistently because you must account for human error, room temperature, all of these other variables that cannot be controlled unless you're in a vacuum. So that's all I have. Here are some of the sources that I used and included for both pictures and then also just for additional research. Thanks for listening, and I look forward to chatting with you guys in the replies. Thanks. Bye.